Good afternoon, everybody. Welcome back to lecture number 36. How was the exam? So exam, probably most likely the final exam will probably include only problems. I don't think I would include conceptual because you always have problems with conceptual. Okay? Except the written conceptual. Written conceptual, it's going to be there, but I don't think I will have MCQ or both. Okay?
The final?
So, what do you want the final? Comprehensive?
No.
Why?
Because
So, it's a proposal. Think about it. The material might be only problems from major one and the quiz. Just change the numbers. Only problem from major 2 and the quizzes. Just change the numbers. And the final.
If it was comprehensive.
It's still comprehensive, but I'm not going to bring كل البروبلمز for that. The only required examples for comprehensive is the examples that came in the test.
Oh.
Maybe I change the numbers a little.
You uploaded the key solution for major 2 or?
I upload. TA is working on it.
Oh.
But let me think. But as of now, it's still comprehensive. يعني ما ألغينا شيء. It's to make things easy.
Okay.
So last time we talked about the counter current braking, okay? What was the counter current argument? The counter current argument, basically, you reverse the direction of IA. It's called terminal voltage reversal. By reversing the voltage direction, IA would reverse. What will happen if IA is reversed? Torque was positive. What will happen to the torque if you reverse the direction? Torque is the K phi times IA. It will be negative. You see it? And then what will happen to the speed? You have a different speed curve. So basically what will happen is if you're operating at this speed and you apply TVR, what is the extension of this curve? Here. So you will jump to this speed at very high torque or high current, negative, and then you will slow down all the way to the point where you want to stop at 0. Get it? So the extension of this line is where you jump from, and then you slow down, slow down, slow down. What is the problem with far extensions? Very large current. So if you have a very large current, it will cause very problems. And how we do the voltage reversal? Using power electronics. Similar sequence to quadrant, the 4-quadrant control operation. So last time we discussed that this curve, if we change the speed from 1 to 2, this 2 will have a current of minus V1 minus E1 over RA. This is a very huge current. And if you want to stop at 0, okay, this is you stop at 0 here. But here if we want to apply negative speed. If you want to stop at 0, you put some sensors and then you disconnect everything at 3 and the motor will stop. If you do nothing, it will keep slowing down, slowing down, slowing down until it goes to point number 4. If it goes to point number 4, it will apply the negative voltage to the load. And this is pretty much similar of holding the constant torque. To hold the constant torque using DC motor, you need to apply negative current. Okay? So what are the relationships? This is the typical relationship at point number 2. Point number 1. Point number 2, your V1 will be negative. Your V1 will be negative. Why it's negative? Because it's quadrant 2. What will happen to point number 3? Speed is 0. Speed is 0, EA is 0. Then you have this current. The current at point number 3 which is this point, is still very high for a zero speed. It is still very high. So 2 is higher, 3 is also high. What we're gonna do right now is, can we put 2 somewhere here, 3 somewhere here, and 4 keep it the same? Yes, by adding resistors. So adding resistance in series with the reversed voltage, we call it here RB. So here at point number A, this is motoring mode. If you go to the TVR braking, you add a negative supply and RB. This makes your brake more, I would say, more efficient to avoid copper losses, and it will achieve the same speed curves. You want to achieve the same speed curve. Okay. You can walk, yeah. You can walk. Doesn't matter. So what will happen here when the braking resistors to be added to the circuit, the current will be smaller and the motor will work on line 3-4. This is line 3-4. So here, instead of jumping directly to point number 2, we jump to, okay, he's putting different numbers, but this is 3, which is the previous 2. And then you can achieve the same results here at point number 4, or you even can go to the negative, very negative speed. So how the math works is you basically, pretty much you apply the equations and you find that RA, it will be added to RB. If RA is added to RB, if you go to point number 4, the relationship will be this, and RT is the same, RA plus RB, and I4 will be smaller than this point, I4 here. So do you remember this table? I don't like this table much, but this is the direction. So at point number 1, everything is positive, 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 positive. We still keep the field, it doesn't matter. During the generator mode, you reverse the torque, you reverse the terminal voltage, you reverse the armature current, but the speed is still the same. The speed 1 and 2, it's the same y-axis. For the holding position, which is number 3, you hold it at speed 0. What will happen is you have negative motor torque, negative voltage, negative current, speed is 0, EA is 0. For the reverse motor, which is the negative, it will be everything is negative except the field. That's how to read this table. So here is a numerical example. Let's look at it real quick. A DC motor has RA 1 kilo ohm, K flux. This has a unit of 3 voltage seconds over the radian. So in the test, what was the K flux that I brought? It was in voltage over RPM. Voltage over RPM, not RPM. Yes. Here it's voltage times seconds over radians. When the TVR is adjusted to 320 volts, okay, the speed is 1000 RPM. A TVR braking is applied. Calculate the braking resistor that would reduce the minimum braking. Here is a typo braking. Here is a typo current to twice the rated value. So what was for induction? Do you remember the braking? What was the value? 2 times or 3 times the rated current? 3. So in DC machines is what? 2. This is one of the rules of thumbs. For DC machines braking, you should not exceed twice the rated current. For AC machines or induction machines, you should not exceed 3 times. This is a rule of thumb. Try to keep it in your mind. If you forget it, that's okay. I do not think everybody knows this information, but over time, if you work in EVs or something similar, you will develop such a habit. Okay? I actually didn't know these 2 numbers, 2 and 3, until I started teaching the course. It's not important. But the rule of thumb is it has to be twice the rated value. Why this is, why twice? Because in the AC, the RMS value is 1 over 1.144, 1 over square root of 2. But for DC, it's always constant. That's why it has to be lower. Otherwise, we will burn the motor. And we will, if there is a permanent magnet, we will demagnetize it. So IA under normal operation, point 1 is 6 amps. Point number 3, it has to be at 12 amps, so it shouldn't exceed 12 amps. So you solve this equation by adding RB. RA is already 1, and here you apply a negative voltage. So you look at point number 3, and do not confuse yourself. Point number 3 has actually this equation, which was point number 2 before we put the line. Or the equation is written here if you go look at the scale. Point number 3, you use this equation, one variable, solve it, 51.8. The other type of braking, which is point number 2. Any question about TVR? So if I ask you a question in the test, and this is one of my favorite questions in the test, similar to what I asked you for the induction. What are the DC machine control techniques? One is TVR, terminal voltage reversal. 2 is what? Dynamic braking. Similar to the dynamic braking. We had dynamic braking. TVR, also known as counter. نفس induction, had the same name. But the more common name is TVR. Dynamic braking has the same. What was the key feature about dynamic braking? You apply a parallel resistor or its equivalent using power electronics to dissipate the heat. So your goal is to dissipate the heat. So dynamic braking is used to stop the motor by dissipating the kinetic energy into a resistive load or equivalent. Why did I say or equivalent of a resistor? Because we have. If you know nothing, just say power electronics. Anything, a smart answer for power, and this is for your interviews. Just say the advancement of power electronics, and you will be fine. Because everything has moved from traditional power, traditional machines control, everything thanks to the power electronics has shifted to MOSFETs and IGBTs. Nobody's using resistors anymore. So if they ask you why EV chargers now are more important, because of the power electronics. Why EV cars are evolving, because of the power electronics. Why renewable energy is coming now very crucial, because of the power electronics. Every answer to every question because of the power electronics. And the second favorite question, if you don't know, reduce cost. Please, do not lose a job by saying, oh, sorry, I don't know. Okay? Just say power electronics, you'll be fine, okay? This is very important. You pretty much in the next few months, or if you will have interviews, the key advancement of power industry, especially machines and renewable energy, is the power electronics. So, or the resistive equivalent, the motor stops if there is no external load torque is exerted. So if you remove the load, you want to stop the motor, you just get rid of the load, and the equation is minus EA over RA over RB. Where is VT? Where is VT? Ahmed. Wow, where is VT? مختفي. طيب. مختفي ايش معناه؟ Not connected. معناته انه we isolate the motor from the supply. The TVR, what did we have? We still had the supply. So this is a major difference between dynamic braking and TVR or counter current. So never ever in dynamic braking connect the batteries. This implies in practical application, if you have a DC motor for EV, you have to isolate the motor from the supply. That's why we have this equation minus EA over RA over RB. It's physical isolation. And how to achieve it by? Power electronics. By power electronics. Nobody is having a breaker on and off. By MOSFETs. The 4-quadrant operation, do you remember the off? There is on off for every quadrant. Use the off settings, which is the 2 diodes have to be on. Or one IGBT has to be depending on the region. Okay? And you can estimate the dissipated heat using V square over R. This is V square over R, or EA square over R, using this equation. And how to achieve it is pretty much using power electronics. You switch from A to B. It doesn't mean you move the breaker for you. You're using power electronics. Pretty much by designing RB, you can control the braking curve. And the good thing about dynamic braking is at zero current, there is zero speed. Why at zero current would be zero speed? Why in the TVR, at zero speed, it's not zero current? صح? Because the supply is already connected. Here, because the supply is not connected, it's a dead motor. It's what?
Dead motor.
Dead motor. That's why you have to go to the origin. You have to go to the origin. Okay? Don't confuse yourself. So moving the switch from A and B using power electronics will disconnect the motor supply and connect the braking resistor RB, and depending on the design, slope of it, you can dissipate heat. So the higher the resistance value, the lower the braking current. Yeah, it makes sense. V equal IR. The higher the resistance, the lower the current, because the voltage is kept constant until we speed to zero. Pretty much Ohm's law. The smaller the braking resistance, the higher the braking current and faster stopping. So what's the problem if you apply a short circuit? It causes fire. And you can apply it. If you apply a short circuit to a lamp, it will cause fire. That's operating. Okay? So, there is another application, what we call dynamic braking for gravitational load. What is a gravitational load? A hoist. A gravitational load is very tricky because if you apply dynamic braking, please turn off the phone or put it in the silent. If you apply dynamic braking, what will happen? It will go to the other quadrant. It will not stop at zero, even if there is no supply. So it will bring back the motor to life. It will enter into regenerative braking of reverse. And then it will swing back and forth between the two regions until it settles down after some time. So you have to be careful for gravitational load torque, like a hoist. When the supply is disconnecting, the operating point will be suddenly changed from A to B. Then the machine speed will decrease until it goes to zero, and then it will start increasing in the other direction because of the gravity. So what we do is we have a mechanical latch. What's the solution? Mechanical latch. Mechanical latch is it will, at zero speed, it will detect. When the speed is zero, it will disconnect the motor, and mechanically it will hold it. So this is pretty much application of mechanical engineering. No need, supply is disconnected. You can't do anything. You need to have mechanical latch. What's a typical type of mechanical latch? Spring. Spring will hold it so that it will dissipate the power. Okay? So this is the table that I told you is not that important. This is a small important DC motor of previous example is loaded by gravitational load. Okay? The motor current is 40 amp at steady state condition. If the DC source is replaced by a braking resistance of 2 ohm, calculate the motor speed. So it's very simple. You use this equation for dynamic braking. You need to get omega. If you solve for omega, you already have K phi from the previous questions, 3.93. Is it in RPM? 3.93? Yeah, I think if you convert it, it will be 3.93. Okay? I want you to verify, maybe this number is wrong. Let's convert. How to convert from 3 times to pi over 60. No. I'm not going to do it this way. I'm going to use this equation. IB equal minus K phi, this is in RPM, times N over 0.377 plus 2. Let's solve it for N. $40 over minus 3 times 0.372 plus 2. No. كم كان الكونستنت؟ I don't think he meant this example. Because RA here is 0.377, it's not 1. So he didn't mean this example. So I think he meant, نشوف الإكزامبل اللي عنده 3.7 هو I think 10.
Yes, 10.
Yeah, okay, it's 10. So how to fix this question, please? Example 10. So the DC motor of example 10, please fix it in your notes. Okay? It's not example 11, example 10. This is wrong. Okay? That's why we have the recording to capture. So please keep in mind the other example. Okay, here we have example number 12. Here we have example number 13. A DC motor has the following data. Calculate the braking resistance required to stop it if it was at 1630 RPM, given that the motor current has not to exceed current where the load torque is 180. How to solve this example? First get omega 0, the base speed is 168. So is the speed, it's working at 630, is it higher than 1600 or lower? Higher. So one question in the test, the last question, true or false? The one before the last one. What was the question? In the generator mode, speed is higher. Okay, so it was true. Both, even the last question was true. So the base speed is higher. So what's the torque at the rated torque is 89. This is the rated speed, this is the rated torque. So the K phi, calculate K phi is 1.22. After you calculate 1.22, you have to solve this using the equation IARA over the K phi. If you plug the numbers, it's IART. So IART is the voltage. So this is like EA equal K omega, which IART equals to the torque times the 180 times the resistance over K phi squared. This is if you substitute certain numbers. It will be 1630 times pi over 3, which is omega base, 1630 times 2 pi over 60. It's the same thing. If you solve it, you'll get RT to be total to be 1.4. And if you subtract the armature resistance of, I think, 0.167, you get 1.233. So here, did he say has not to exceed twice the current, or he said not to exceed the current?
Not to exceed.
Not to exceed the current where the load torque is 180. So what does that mean? It means we're applying a stricter condition than twice. Okay, sometimes we apply such statement, or not to exceed twice, then you multiply by 2. Twice the current, then it will be, what is the current? It will be 2IA. The last part is, so any question about these examples of dynamic braking? Clear? واضحة? Pretty much the last example, I don't think it's a good example. I think this example is better. This example is not a good example because it uses equations that somehow we didn't state specifically in the formula sheet. So I would say example 13, hopefully it will not sure, hopefully it will not come in the test. Like when I write the exam, probably I'm not gonna look into that example, okay? Because it uses this simplifications, T times R. Anybody knows why TA times R over K phi squared? From where you got it from IA equal torque over K flux. So if you replace IA with this one, you will have the T over K squared. So you have 180 RT over 1.22 squared, and then you solve it. Question is clear, but I do not like it because if I told you the current has not to exceed twice the rated, why here I tell you has not to exceed the current where it's at 180? The last slide of DC machines is solid state breaking resistor control. So a variable resistance can be achieved using semiconductor, which is in parallel with ohmic resistance. So this is one way of applying hybrid. We can have a resistor in parallel with the power electronics. How does this solid state breaking? So what's the third type? Solid state breaking resistor control. So here we use the beauty of power electronics in parallel with a resistor. This is a mix. By using DC chopper, we have, first of all, is this connected to the supply or not? During the breaking, do you see battery? So it means this is similar to dynamic braking. ما في عندي supply. How did I isolate the supply?
Using power electronics.
That's it. Okay, that's how you need to operate. Using power electronics, we isolate the supply. So this is the equivalent circuit. So I already have a resistor, I already have another MOSFET, and I have my machine. This is the feed on the side. I apply a second quadrant, so I'm operating at the second quadrant. So during braking, I do not send how can I say it? So IA is always constant. IA is always gonna be there. It will be split either IC or IB. When IC will be on, if the gate of the MOSFET is on. If the gate is MOSFET is on, this will be short circuit, so all of the current will go here. Under which conditions it will go here? So IC will equal to IA under this region and under this region. So between time KT and T, I turn off the MOSFET and I make IA equal to IB, and I have a voltage drop across the resistor. So during this, the MOSFET has to stay on all the time. The moment it's off, the resistor would have a voltage drop of RBIA, which is equal to VB. So what's the idea behind this trick? Instead of having variable resistor, I can send pulses. If there is short circuit, if the current goes here, it will circulate back, and it will not do braking. If the resistor is active, which is during that rectangle, I'm going to have power dissipation across the resistor. So if the MOSFET is on, no braking. If MOSFET is off, there is a braking. Clear? So to know that IB would equal to IA times 1 minus K, which is 1 minus the duty cycle, If you plug it here, it will be EA minus IA. Apply the math, R equivalent with. So now we're changing the RB, not to be RB all the time. We're reducing its effective value using power electronics. So using power electronics, the only difference is I square R, the power dissipated is I square RB times 1 minus K. So the factor 1 minus K is a control factor that if you make K 0, what does it happen if you make K 0? This pulse will be on all the way. If this pulse is on all the way, all the current will go through the resistor. If I make K bigger, the power dissipation will be smaller, and I make this pulse smaller, so all of the current will go through the MOSFET, and no breaking will happen. Quick question. Do I have higher losses at the MOSFET or at the resistor? Because MOSFET acts like a switch. So I want you to understand this, how it works. Maybe one question in the test, explain using your own words how solid state breaking resistor control works. With that, we finish DC machines, and we have, I'm not going to start the new chapter, but let's look at the syllabus. Let's look at what's left, and then we'll end the lecture early today. So what did we finish? We are at week 13. Okay, so we are pretty much late now by how many weeks? We should have started variable speed drives.
No.
However,
We're in the end of week 12.
Yes.
we're in week 12.
Yes.
Okay, so we are late still by 3 weeks. But what I'm gonna do is I'm gonna hopefully we can finish these 4. So the applications is hopefully gonna be replaced by the guest speakers. Okay? The applications will be replaced. And who cares about drives, application, and renewable energy? I think it's better for you to know the basics. So the applications will be replaced by the guest speaker. Hopefully the second guest speaker agrees, and I think he will talk to us about those applications, okay? The special machines, universal motor, single phase stepper, we will talk about it. Hopefully 2 weeks is more than enough. The variable speed drive, we will touch base on it. We'll not talk much about it because it's covered in E460. We're not going to go into the math. So I will probably reduce the number of examples to accommodate such things. But I think the last week, the application is not going to be renewable and smart grids. I think the application, if the guest speaker agrees to give his speech, it will be in EV charging stations. How the drives used in EV charging stations. Do we all know how the drives used in the machine? But we don't know about the drives working in the charging stations and the other EV infrastructure. Okay? With that, we will finish today's lecture. We still have 10 minutes left. I leave the floor to ask about the project. How's the progress in the project? Anybody got the project working? Huh? Okay, last time in the exam I discussed about the presentation. I told you at the beginning we're going to have it online, but I changed my mind. Why did I change my mind? Because I believe if you do the presentation in person, you will be more nervous and you will learn more. And I want you to learn. I'm not going to take off points. Okay? But if you do it online, you're going to waste more time. You're going to record and then, oh, I don't look good. Oh, I didn't say the right word. And you keep wasting 3 hours. Just come and present and go. Okay? Okay?
Which day? 16?
No, you can choose. You can choose any days.
بعد الفاينل بعد
Maybe, yeah, before, I prefer before the final. Yani, don't defer the project, but we can, yani, I will open some openings every week, maybe 1 hour every week, and then you can come present 5 minutes and go, or present in my office. I do have monitors. Or we will come to any classroom and present as a group. If you're not comfortable, you can present after class, okay? Come to the classroom. We can, or during classroom. It's an option. So if you want to present in front of the class, you can come present in front of the class. We'll leave the last 5 minutes for your presentations, okay? Try hopefully to attend the grade exam. Give me a week, it takes time. Any other questions? Tamam? So how does it look like, the future chapters? It's pretty much heavy. But we will start with, is it a universal? Yeah, universal. We'll start with the universal motor. These are the original slides from Dr. Abu Bakr Salim. So this is the universal motor. This is how it looks like. We'll start talking about it next lecture, okay? What do you think from its name, universal motor?
What's with AC and DC?
It's mixed use. AC, DC, three-phase by design, okay? So we'll talk, inshallah, start talking about it in the following lectures. Please do not skip the guest speaker. Write it in the WhatsApp group. If you want to bring, if you want to dress professionally, that's even better. You don't know, maybe this guy will be, somehow you'll have a business with him in the future. Who knows? Okay? Tawfiq, inshallah.